With this video, we enter the exciting world of multi-step synthesis, including the reactions we learned in this alpha carbon chemistry chapter. Now, there are a couple patterns that are worth learning, a couple patterns that will make these multi-synthesis questions or exercises much simpler and more straightforward. And the first one of those is recognizing di-functionalized compounds. Those are compounds that have two functional groups on them. Now, we learned three different ways to make these di-functionalized compounds in this chapter. The first way was the Aldol Addition. So if you had an aldehyde or a ketone, a base would steal the alpha hydrogen, turn it into a nucleophile, and one of these could attack, that alpha carbon nucleophile could attack a carbonyl carbon electrophile in another version of that molecule. And what you end up with is the carbonyl, whose alpha carbon was the nucleophile. So you have the carbonyl, then you have the alpha carbon, and that attacked the carbonyl of another version of itself, whose pi bond broke, and whose oxygen then got protonated. So the Aldol addition gave us two functional groups. They were 1,3 to each other, and one of them was a carbonyl, and the other one was not. Compare that with the second way we learned in this chapter, how to make a molecule with two functional groups. That was the Claisen condensation. The Claisen condensation, instead of using two aldehydes, used two esters. A base, and the base had to match the alkoxy group of the ester, so that if it did do a nucleophilic acyl substitution, it didn't change your original molecule. So you use a base that would rip off a hydrogen from the alpha carbon, turn that alpha carbon into a nucleophile, where it could then do a nucleophilic acyl substitution with another ester and replace the leaving group on it. So this whole thing is the sort of nucleophile, the alpha carbon nucleophile, that came in and replaced the ethoxy group that used to be here. And notice what you have here. When you do the Claisen condensation, you have two functional groups. They are 1,3 to each other. If you start counting from one to the other, it's on carbon 1 and 3. And the oxidation state of both is they're both carbonyls. You have two bonds to oxygen on each of the functional groups there. So that's the Claisen condensation. And the last way we learned how to make a difunctionalized compound was with the Stork Enamine synthesis. Now, this one was unique because it gave us two functional groups that were 1,5 to each other. So if you start numbering at 1 and walk your way to the other, you'd have them on carbons number 1 and 5. And they're both carbonyls. So this little table here, you might copy it down for your notes. It'll be useful to think through or to refer to as we go through these exercises. So hopefully by now you'll know the reactions themselves, you'll know the recipes and what happens to them. Now you're just adding this sort of connection in your mind, that if you see difunctionalized compounds, you're going to think of these three reactions. If the two functional groups are 1,3 to each other, then you'll think of the Aldol condensation, the Claisen condensation. If they're 1,5 to each other, then you'll think of the Stork Enamine synthesis. And to choose between the Aldol and Claisen, think about how many bonds to oxygen you have. If you just have one carbonyl, it's the Aldol. If you have two carbonyls, it's the Claisen. All right, so let's apply that to the exercises the exercises in exercise 2251. Okay, so you look at this crazy molecule, and what's the first thing you should notice? The first thing you should notice is that you have a di-functionalized compound. It's a unique thing. And how far are these difunctionalized compounds from each other? Well, let's start counting. 1, 2, 3, 4, 5. They're on carbon 1 and 5. So you'll remember that a 1,5 difunctionalized compound, you can make that using the Stork Enamine synthesis. So we're going to use an amine as the first step. We'll have water to hydrolyze the last step, and then in the middle we'll have that alpha-beta unsaturated aldehyde or ketone. Okay, so Stork Enamine synthesis. Now in the Stork Enamine synthesis, we need an alpha carbon to act as a nucleophile, and a weak nucleophile. And then we need a beta carbon to act as an electrophile. And we could technically use either one here. I'm going to use this as the alpha carbon that acts as the nucleophile. And then going in the other direction, we have the alpha and beta carbon. This is where I'm going to have the unsaturation. So the new bond we're forming will be this bond right here. So I'm going to break that bond to try to visualize the two pieces I need to bring together here. And I'm using this as the alpha carbon, where theoretically you could use both, because in the problem they say using cyclopentanone as your starting material. So if you draw that left part, you'll notice that that is cyclopentanone. And there is no alpha-beta unsaturation here. So this is going to have the alpha carbon acting as our nucleophile. So that's that molecule on the left. Okay, if we look at the molecule on the right, if we copy that out, separated from the other piece, I'll draw it so it looks a lot like what's there. If we look at this, this is where we have the alpha and beta carbons. Alpha and beta carbons. And to make this alpha carbon nucleophile attack this beta carbon electrophile, we have to have a degree of unsaturation here. So you have to draw that pi bond in between the alpha and beta carbons. Now a carbon in an alpha beta unsaturation, or a carbon in a double bond, is trigonal planar. So this should really be pointing out to the ends of a triangle, these bonds there. So I'm just going to redraw that so it looks a little bit more like what the molecule actually looks like in 3 dimensions. Okay, so those are our two pieces. Now if you remember, in the Stork enamine synthesis, the first step is to turn this into an enamine, because right now, if you just treat this with a base to steal the alpha hydrogen and turn the alpha carbon into a nucleophile, that's a strong nucleophile and it will attack the carbonyl carbon, not the beta carbon. So we have to turn it first into a weak nucleophile. And so to turn this into a weak nucleophile, we'll turn it into an enamine. You turn a ketone into an enamine by treating it with a secondary amine. So a secondary amine has 2 alkyl groups, and then just to make that happen faster, you use an acid catalyst, and to improve your yield, you remove water from the products. That shifts equilibrium to the right using Le Chatelier's principle. So that would turn that cyclopentanone into an enamine. You'll notice that the nitrogen still has the 2 carbons bonded to it. That's what those capital R's are. Oops, and this should just have 1 hydrogen. The 1 hydrogen got replaced by the 1 bond to what was the carbonyl carbon. And you drew the mechanism for that in a previous chapter. If you want to see how that happens, the mechanism for how that happens, you can see a video in the aldehyde and ketone chapter for enamine formation. Okay, well, once you have that enamine, your alpha carbon is a weak nucleophile now, and so you can treat it with this alpha-beta unsaturated compound. That's your first step. Once you do that, you still have an iminium ion on there, so you sort of have an enamine derivative after you add that, and so to hydrolyze that, you can use water or hydronium. I'm going to use hydronium to hydrolyze that, and also to help get the other carbonyl back, because that turns into an enolate. And we've seen those steps in previous videos. Once you do those reactions, the alpha carbon here connects to the beta carbon. So I'm going to move this up again. And I'll draw this in orange. And just erase that pi bond. And you'll notice that that is the same exact molecule that they wanted us to make. So the key here was noticing that you had 2 functional groups. It was a di-functionalized compound. And then once you saw that, to count how far the 2 functional groups are away from each other, when you saw they were 1, 5, it would be the Stork enamine synthesis. And from there, it was just a standard retrosynthesis for the Stork enamine synthesis like we've done in a previous video. So altogether, the sort of recipe you'd use here is you'd start with, let me make these a little smaller. So you'd start with cyclopentanone. And you'd treat it with first a secondary amine in the presence of catalytic acid and the removal of water, so minus H2O. That gives you the enamine. Then, once you have that weak nucleophile that will attack the beta-carbon, you can treat it with the appropriate alpha-beta unsaturated ketone that we figured out by looking at analyzing the original structure. And then you just do an aqueous acid wash, so hydronium. That takes off the enamine, turns it back into a carbonyl, and turns the enolate that you have into a ketone through ketoenol tautomerism. So the whole recipe would be that beautiful haiku right there. Okay, let's try it again with B. Same sort of process of thinking, very different molecule. You'd look at this and you'd say, oh my gosh, I have two functional groups, one and another. And the functional groups should stand out because you'll have letters drawn in. Functional groups almost always have what are called heteroatoms, atoms that are different, hetero, from carbon. So nitrogen, oxygen, sulfur, etc. So look at those. You see, whenever you see letters in your molecule, you're like, oh, I've got functional groups. If you have two of them, then you have a di-functionalized compound. Highlight those and then number them. Starting at 1, how far is the other one? You'll see that here, your two functional groups on carbon numbers 1 and 3. Now that narrows our thinking down to the Aldol addition and the Claisen condensation. Both of those have 1,3 di-functionalized compounds. The difference between them is how many carbonyls you have. In the Aldol addition, you have just 1, and in the Claisen condensation, you have 2. So, in this, we have only 1 carbonyl, and so we know that we're going to be doing the Aldol addition. So what we need in the Aldol addition is NaOH and water. Okay. So let's think about how this works. Now we know the problem told us we have to start with cyclopentanone. So if we have cyclopentanone, and we treat that with sodium hydroxide, let's think about what would happen. The hydroxide is really the reactive part of that molecule. It can act as a strong nucleophile or a strong base. Here it's going to act as a base because we have a vulnerable hydrogen for it to rip off. It can steal that hydrogen there, it can snap onto that alpha carbon, and so we would create this nucleophile on the alpha position. And actually let me use purple there because that lone pair is from the bond. So that can act as a nucleophile. Okay, let's highlight that in the original structure so we see what else we have to accommodate. So let's say, okay, this is cyclopentanone. What else do we need? We need the rest of this. Now, what you see here is that this nucleophile will need an electrophile to attack. You can see that it's going to attack that carbon, right? This nucleophile attaches to that carbon, so that's the one that it attacked. So I'm going to redraw this molecule. But how could we make this carbon an electrophile so that this nucleophile will want to attack it? Well, we can turn it into a carbonyl. If we've learned anything in the last few chapters, it's that a carbonyl carbon is an electrophile. Now, to create room on the oxygen, we have to get rid of this other methyl group on top there. And so once we get rid of that, and we'll have to put that back somehow, but once we get rid of that, we could have that pi bond, and we don't want to add any more carbon, so I'll just have a hydrogen there, so this is an aldehyde. And so that aldehyde gives us an electrophile on the carbonyl carbon for our alpha carbon nucleophile to attack. And the pi bond would go up, and what we'd get would be that lone pair forming a new bond to this carbon. Now there's only one bond to the oxygen because the pi bond broke, so the oxygen will have 3 lone pairs instead of the 2 that it had, and therefore a full negative charge. And the rest of the molecule is unchanged, so now we have this. Okay, well, here we are at this point in the synthesis, and we have this oxygen here with a full negative charge, which is unstable, or another way of saying that same thing is it's reactive. And maybe it's useful that it is reactive because we're not done yet. We don't want to do a proton transfer to stabilize that because we don't have an H there. We have a methyl group. And what you'd recognize, what you would see in that negative charge is a nucleophile. So how can we attach a carbon onto that nucleophile? We can turn a carbon into an electrophile. We can just add an electronegative atom that is also a leaving group, so a halogen, chlorine, bromine, or iodine, and do an SN2 reaction. This is the Williamson ether synthesis, way back from chapter 14, the first chapter, one of the first chapters in this course. So that can attack the carbon, kick the leaving group off. Oops, it should start from these electrons. And at the very end there, you'll end up with that final product that you want. So these two are really the same. So overall, the sort of synthesis that we need, here I'll write it in green here in the middle. The first thing we have to do, we'll take our cyclopentanone, which we had to start with, and we will treat it first with sodium hydroxide. And we could see that will turn that alpha carbon into a nucleophile. Once we have that nucleophile, we can react it with the aldehyde that we saw. Once we have that aldehyde, we can just do an SN2 reaction by treating it with methyl iodide, or methyl chloride we have here. So this is the CH3 there. And it could be any leaving group. I said iodide just now. It could be iodine, it could be bromine. Any leaving group would be good. And so that is the recipe to create this reaction using what we've learned in this chapter. And the key to it all was recognizing that we had a difunctionalized compound and the two functional groups were 1,3 to each other. And we only had one carbonyl. That narrowed it down to the Aldol addition. Okay, let's try one more multi-step synthesis in this video. So you'd look at this next molecule and you'd say, ay caramba, I have 2 letters in there, 2 places where letters are written in. Those are functional groups. So this is a di-functionalized molecule. Well, I can narrow down what I need to do by numbering the carbons between these. The first functional group is on carbon number 1, the second one is on carbon number 5. Now notice, these are not carbonyls. Nonetheless, we have 2 functional groups. We know that all functional groups can be changed into each other. So maybe these could be made from or turned into carbonyls. And they're on 1,5. Well, that should remind you of the Stork enamine synthesis. The Stork enamine synthesis gives you 2 functional groups on carbons number 1 and 5. Now it's true, the Stork enamine synthesis will give us 2 carbonyls, but we can always change the functional group into whatever we want using our competence as organic chemists. Okay, so how would we do this? We know that just from that preliminary analysis that we have to do the Stork enamine synthesis. And we know from the prompt for this exercise that we have to start with cyclopentanone. Oops. At the very beginning, this exercise says using cyclopentanone as your starting material. So we write cyclopentanone in. What we know about cyclopentanone is, sure, its carbonyl carbon is electrophilic, but we can easily turn the alpha carbon into a nucleophile. Now, if we did turn this into a nucleophile, let's sort of visually organize the product we're trying to get, compare it to what we know we have. So what else do we need to add? We need to add that whole group there. Well, we know that this alpha carbon can be nucleophilic. And we know that we have a 1,5 difunctionalized compound. So let's think in the context of the Stork enamine synthesis. What can we do? Well, if we did the Stork enamine synthesis, we would need an alpha-beta unsaturated compound. Now, that's not in cyclopentanone, so it must be in our other piece. In order to have an alpha-beta unsaturated compound, we have to have a carbonyl. Now, I know that's not what we have here, but let's imagine. Use the power of our imagination. And so we have an aldehyde there. That gives us this double bond to a pi bond to an electronegative atom. If you'll remember, that's what causes the resonance that makes the beta carbon electrophilic. And then we would have a degree of unsaturation between the alpha and the beta carbons, right? So this is the carbonyl carbon, this is the alpha carbon, this is the beta carbon. So this beta carbon, if we have an unsaturation there, can turn into an electrophile in the Stork enamine synthesis. So we could take cyclopentanone and react it with a strong base, just for the sake of old time's sake. Let's use LDA, lithium diisopropylamide, which we've discussed in previous videos. That strong, bulky base. So that will turn all of these cyclopentanones into nucleophiles. It'll turn the alpha carbons on them into nucleophiles. And then we can treat those nucleophiles with our alpha-beta unsaturated compound. Oh, except, wait a second. The problem here is this is a strong nucleophile. So it will actually prefer the carbonyl carbon. So we have to make that a weak nucleophile, and the way we do that is given in the name. We have to turn it into an enamine. So we take a secondary amine, catalytic acid, remove water to increase yield using Le Chatelier's principle, and it will turn the ketone into an enamine. So this is now a weak nucleophile, and we can react that with, first, our alpha-beta unsaturated aldehyde, and then we would use aqueous acid, hydronium, to take the enamine off, turn that back into a ketone, and promote the ketoenol tautomerism that we need to get the other ketone back. Okay, let's sort of visually organize this before we redraw it. So these are sort of our two pieces if we're relating it to our original molecule. Now I'm going to take each of these. What happens in this reaction is that the alpha carbon turns into a weak nucleophile, and the beta carbon is the electrophile that it attacks. So you end up forming a new bond between these. Now when that happens, this bond goes away, and after you treat it with hydronium, it hydrolyzes the enamine and gives you back the ketone. Now that's a vastly simplified version of that mechanism, but we did discuss that in detail in a previous video. So we're almost there. We certainly have something that looks a lot like the product we want. If you compare this with the thing that we want, up in the top left, it's almost the same. We just have carbonyls where we want alcohols. So here we have 2 bonds to each of these oxygens. The molecule we want, we only have 1 bond to each oxygen. Wait a second, we want to reduce the number of bonds to oxygen? That is a reduction. So what we can do is use a strong reducing agent like lithium aluminum hydride. Anytime you use lithium aluminum hydride, you want to follow it up with a water wash to stabilize the oxygens by doing a proton transfer. And that reducing agent reduces the number of bonds to oxygen. So you only have 1, and the water puts an H on each of those. Now, I'll get rid of that hydrogen there. It's still there. It's just implied in the structure. So you'll notice that what we end up with is the exact molecule that we wanted. So the trick here was looking at this original molecule and seeing that we had a di-functionalized compound. Then we counted the carbons between the 2 functional groups. We saw they were 1,5, and that was a strong suggestion that we should use the Stork enamine synthesis. The prompt said we had to start with cyclopentanone, so we did the Stork enamine synthesis with that. We used the secondary amine to get the weak nucleophile, and then we figured out the alpha-beta unsaturated aldehyde we would need in order to add this correct number of carbons on. Once we did that, we had 2 carbonyls, whereas we wanted 2 alcohols, so we wanted to reduce the number of bonds to oxygen, so we used a strong reducing agent, lithium aluminum hydride, followed by water. And that gave us our product. So overall, the recipe you would want to use is you'd want to start to create that molecule there from cyclopentanone. Is starting with cyclopentanone, you would first create the enamine by adding a secondary amine in the presence of catalytic acid and removing water to increase yields. Then you would use the alpha-beta unsaturated aldehyde that gives you the specific molecule you want, followed by aqueous acid, so hydronium, and then in the last step, reduction. So first, lithium aluminum hydride, and second, a water wash to stabilize any charges. And that beautiful recipe will create this magnificent product. So, hopefully these 3 exercises helped to illustrate the concept that using these 3 patterns of di-functionalized compounds helps you to narrow down which reactions from this chapter you would use to achieve a certain transformation.